Okay, thanks for the kind introduction. Thanks for being here. So, as already said, I'm going to talk a wee bit about the possibilities and challenges we are facing when using AI in conjunction with hyperspectral data. EVK is a small company from Austria. We are family-owned business, and yeah, we are out there since almost 40 years. And initially, we are coming from the sensor-based sorting and control and inspection business and community, where we are using our own proprietary sensor technology and software to bring solutions to our customers, predominantly in the food segment, also recycling industry, chemical industry. And we also have offices in Korea, as well as we are operating in Italy. We consider ourselves as an expert company, predominantly in hyperspectral imaging, which we are having since almost 20 years now as a technology. So yeah, 2006, we were amongst the first to deliver hyperspectral into the sorting business as a classifying system. So where you have onboard classification, just as Tobias explained to you, where you have a smart camera that actually delivers already ready to use classified data from your product stream. So our core expertise thus is hyperspectral imaging, is also conductivity imaging, so metal detection, also for the sorting business, and our RGB cameras, which we use as a commodity technology for decades now. So our approach is to bring the whole solution to our customer, not a component business. It's a solution-driven business, and that works out quite well. So just in one overview, we have the hyperspectral cameras, the sensors, the conductivity imaging, plus along those lines, we bring the software that you need to do real-time data processing. If you are in the factory, if you have a bulk stream of product, of material, and you want to analyze it in real time and within milliseconds, to be precise, to arrive at a sorting decision, you need all those components, and they're coming from one hand. You do not have to buy it from different vendors. You come to us and you get the turnkey solution from one hand. So we use it, as I said, for the sorting, but also in inspection and monitoring it's used, where you do not need a sorting unit, but want to know more about your material, also quantitative information if needed, and industrial data analytics is also part of it. So we serve the food market there, foreign body removal, for instance. If you eat French fries, it's very likely that they have been inspected with one of our cameras, that there are no foreign bodies in there, that what arrives at your plate is something to eat and not something disgusting. It's also used in mining, where you differentiate between minerals and, let's say, gangue material that you cannot use in the further process. Of course, recycling. Everybody knows that we are separating our litter and try to reuse, use those resources a second time, also used as refuse-derived fuels for incineration, not to use, let's say, carbon fuels. Also a little bit of pharmaceutical applications that we were involved in. Yeah. So just to give you an example, this is I think a well-established technology by now. For some it might be new, but as I said, we use it for almost 20 years. It has arrived in the industry, it's field proven, it runs in several hundred sites over the world as we speak. For instance, here this is an example where we infer quantitative measurements in real time from a product stream. In this case, it's refuse-derived fuel that you use, and you want to know different quality parameters that classically have been inferred in a lab, but by transferring with algorithms such measurement onto the cameras, you can infer quality parameters like calorific value or humidity, which is important if you want to use this material for incineration of a kiln, for instance, in the cement industry. The same, here's a typical sorting application like paper sorting, where typically in the sorting business not only one sensor technology brings the solution, you have to fuse different sensor streams to arrive at a thorough sorting decision. That's what we're doing. We combine hyperspectral here with color cameras together in our fusion engine, and this can be built into an optical sorter. Okay, so this is what we have been doing so far, and this is our bread and butter applications. Now I'd like to talk about the possibilities of artificial intelligence also for our data streams, because of course the sensor technology is quite evolved, but not all problems in the field can be solved with it. And the hypothesis is because we are not able to harness all the information in the data with, let's say, textbook and state-of-the-art machine learning algorithms. And the promise of artificial intelligence would be to bring out more information from the data streams we already have. And that's where we are looking at the moment, what we are testing in the field and in pilot plants. And just to get the idea across, what's so special with artificial intelligence, it's not really new. I mean, neural networks exist since, I guess, since the 40s. But what's new is the computing hardware that is strong enough to process this data now. And what deep neural networks particularly are doing is they can infer features that are not accessible in a classic way for human beings because the amount of data is too vast, is too high dimensional. And if you look into the different layers of such a neural network, you see that the AI detects the same features like a human being, but the deeper you go, the more subtle differences that you see in the data can be inferred by this technology, where human beings are not able to see, let's say, high-level correlations that are still worthwhile being used, and if they are stable and causal, might be used in a technical process. So that's basically what we're doing. We take our own data, our hyperspectral data, and feed it in deep neural networks as they're available. And our results, classification results, are, let's say, better in many respects, in the sense that we now can use a broader feature basis, which has been, let's say, defined by an engineer in the old days and can be automatically retrieved by means of this technology. Of course, the data in the industry is very complex. If we think about recycling, for instance, there are so many different materials, there are so many different conditions, humidity, dust, vibrations, whatever, that the phase space is really huge. And that's, for one part, an advantage where AI comes in handy, because it is able to extract all those subtle differences in the data. On the other hand, it's also, let's say, a door for biases that you have to accommodate, because such a technology will always be error prone if you don't know what you're doing, if you do not differentiate between information and, let's say, signals that are not useful for your application. So that's the challenging part, of course. Just to show you some very promising results, here we have some organic waste that we were not able to differentiate by means of classical algorithms, which now show a very high sorting accuracy. And this is a direct comparison of classical chemometric ansatz compared to what the AI can see. So it should be the left and the very right particles should go in one class, and two in the middle in another class. The AI is quite accurate in identifying them. The classical approach wouldn't be able to do this distinction. On the other hand, this is on the, let's say, positive side. On the negative side is if the AI is more sensitive to such information, it's also more sensitive to biases and faulty signals, subject to your process, subject to changing conditions. And in this case, for instance, humidity is a known factor in NIR spectroscopy that disturbs or can disturb your application. And in this case, it's very important that you have to factor out different humidity levels that can be seen in the material. If you don't do that, you're error prone to a faulty classification. So that's something you have to accommodate by clever pre-processing or by teaching the AI what's a good signal, what's a bad signal, because the AI itself, and that's a disadvantage to human beings, is not able or doesn't have the ground truth what is true and what is a faulty information. You have to tell it. It will not learn it by itself. So there, the domain knowledge of the developer, of the engineer, is still crucial. So AI will not replace us. It's just a very powerful tool, but still us engineers and human beings who have to tell the system what is good, what is bad. This is an example of quantitative measurements in rancid walnuts, where we already use AI on a test bench level, where you can see that walnuts that have higher levels of fatty rancid acids, which you don't want to eat, which you cannot sell, which you don't want to buy, from OK levels. This is all being tested at the moment, so it's development work, but I just want to give you this, let's say, view into the future, what this technology also can do for hyperspectral imaging. And I just want to leave you with the bottom line that in order to bring an application, bring a solution into the industry by using such technology like hyperspectral imaging, it's really important that you infer the key data from the sensor. And it's important that you know your environment, that you know the vital information, and AI for sure is a tool that can help harnessing your data even better. And yeah, I say thank you for